Use the given equations to complete the table of values. So I'll do the second one. We have 5 is being plugged in for x. Negative 2 times 5 is negative 10. And negative 10 plus 7 is negative 3. Then we're going to plug in negative 5 over 2. Well, negative 2 times negative 5 is positive 10. 10 over 2 can be changed into 5. And 5 plus 7 is 12. Then we are replacing the y value with 5. We'll subtract 7. Divide by negative 2 on both sides. We get x equals 1. Fill in the table for problem 1. Which one does not belong? Find a category in which 3 of the items belong, but a 4th item does not. Explain. Well, you might say that B does not belong because all of them have a y-intercept, except for graph B. You might say graph D does not belong because the rest of them form a straight line, whereas graph D forms a curve. You may also say C does not belong because the other 3 are connected, whereas graph C is distinct points. So you can make a claim for any of them not belonging, but you need to make sure that you back it up with an explanation. The distance that Eve runs is a function of the amount of time she spends running. Assume Eve runs at a constant rate of 3 miles in 21 minutes. Write an equation for the function that represents the number of miles Eve runs, y, in x minutes. Well, her rate is 3 miles every 21 minutes. So our miles per minute is 3 over 21. If we stick 1 in the y position, we can multiply the whole equation by 21 to get rid of the fraction. Then divide both sides by 3 to solve it for x. And that gives us x equals 7. Then we can plug in 14 for the x value. Three times 14 is 42. 42 over 21 is 2. If we plugged in 28, 28 times 3 is 84. And 84 over 21 is 4. Part C, the input of the function x is the amount of time Eve runs, and the output of the function y is the distance Eve runs in that amount of time. Write the inputs and outputs from part B as ordered pair, and plot the points in the coordinate plane. In 7 minutes, she ran 1 mile. In 14 minutes, she ran 2 miles. And in 28 minutes, she ran 4 miles. So we need to plot those. 7 is between 6 and 8. 14, 2. And 28, 4. Connect the points you have plotted to make a line that starts at 0, 0. That takes care of part D. E says graph the equation y equals 1/7 x by using the same coordinate plane as in part C. What do you notice about the graph of all the input-output pairs that describes Eve's running and the graph of the equation? So in this, our y-intercept is 0 and our slope is 1/7. So we're starting at 0 and we have a slope of 1/7. So we're going up 1 and over 7, up 1 and over 7. Remember, it's not just up 1 over 7 boxes, it's up 1 over 7. But it makes the same line. So when it says, what do you notice about the graph of all input-output pairs and the graph of the equation? They match. An arcade charges a flat fee of $1.50 for entry into the arcade and charges 75 cents for each game token. The total cost of visiting the arcade is a function of the number of game tokens purchased. Write an equation for the function that represents the total cost in dollars of visiting the arcade, y, when purchasing X tokens. So the flat fee and the cost per token make up the total cost. Identify the input and output of this function. The number of tokens is our input. And the output would be the cost in dollars. Find 3 input-output pairs of this function and plot them as points in the coordinate plane. So if we put 0 tokens into that equation, y equals 0 plus 150, which is $1.50. If we put 2 into that equation, 75 cents times 2 is $1.50, plus $1.50 to get into it would be $3. 4 times 75 cents is $3, plus $1.50 would be $4.50. What do you think the graph of all possible input-output pairs would look like? Explain. It should form a straight line. That has an upward slope. But we won't connect the points. And the reason is because we can't buy partial tokens. Plot all remaining input-output pairs that make sense in this context in the coordinate plane from part C to complete the graph of the function. So we can graph what would happen at 1, $1.50 plus 75 cents for one token would be $2.25. We could buy 3 tokens. 3 times 75 cents is $2.25 plus $1.50 would be $3.75. 5 times 0.75 or 75 cents plus $1.50 is $5.25. 6 times 0.75 plus $1.50 would put us at $6. 7 would put us at $6.75. And then the next one would be $7.50. And then $8.25. And then $9. And $9.75. But we're not going to connect them since we can't buy a half of a token or a piece of a token. Then it says in F to graph the equation by using the same coordinate plane in part C. What do you notice about the graph? So this has a y-intercept of 1.5 and a slope of 0.75. This one extends beyond just the first quadrant, and it goes through all the input-output pairs. But the equation of the line also crosses through partial tokens. Consider a function that takes a number and assigns an output of twice the number plus 3. Write a function that represents this. Write an equation that represents this function. Well, if we're doing twice a number, that would be 2x plus 3. What inputs make sense in this context? Any real number would work. Because it doesn't have a context that says it needs to be a whole number or a positive. C, graph the function in the coordinate plane. This has a y-intercept of 3 and a slope of 2, so up 2 over 1. D, graph the equation by using the same coordinate plane as in part C. How does the graph of the function relate to the graph of the equation that represents this function? They are the same because there were no restrictions on our inputs or outputs. The area of a square is a function of the side length of the square. Write an equation that represents this function. Let A be the area of a square, let the area be A square units and the side length be S units. Well, that would be S times S, or we can write it as A equals S squared. Identify the inputs and outputs of this function. Inputs are the side lengths, and the output would be the areas. Find 4 input-output pairs of this function and plot them as points in the coordinate plane. So if we had a side length of 1, 1 squared is 1. We had a side length of 3, 3 squared would be 9. We had a side length of 4, 4 squared is 16. And if I had a side length of 5, 5 squared would be 25. I'm going to put 2 in there also just because it might help us identify what's happening. 2 squared is 4. So if we try to graph a straight line through here, you can see that it's not going to hit all of the points. What inputs make sense in this context? Well, we can have side lengths that are decimals, but we wouldn't want any negative values. So any number that is 0 or larger. Does it make sense to connect the points? Explain. And if it does make sense, connect the points. Yes, it does make sense to connect them because we can have side lengths that are fractions or decimals. Between the points we already plotted. And since it does make sense, we're going to go back and connect them. This should form a curve. So you can see this one, 2, 4, 4, all the way up to 16. This one shows that curve. Here's what would happen if you graphed the negative side of it, but we don't have any negative values for side lengths. So we miss this whole piece of the equation. This would be the part that we do have. For problem 6 through 11, determine whether the graph represents a function and explain your reasoning. This first one, number 6, is not a function because the inputs of 4 can go to 2 different places. Remember we discussed in a previous lesson that each input can only have one output. Here the input -2 can go to 6 or almost to 6 and then almost to -6. But you shouldn't be able to be located at 2 different places at once. Another way that we talk about functions is using what's called a vertical line test. So we draw a vertical line, and if the graph passes through more than one point on that vertical line at any given time, it is not a function. So since this vertical line is touching here and here, this one fails what we call test. If we take that vertical line to this function here, it only ever touches that vertical line at one spot at a time. So this is a function. Each input goes to exactly one output. If we take this vertical line, you can see that it's touching at two different points, here and here. So this one fails the vertical line test, so it is not a function. This input of 3 has two different outputs. And then the input 2 also has multiple outputs. 1 point, 1 point, 1 point, 1 point, 1 point, the whole way. This one passes, so it is a function. Let's examine number 10. There's 1, 1, 1, 1. It's only ever crossing one point at a time, so this one is a function. Each input has exactly one output. Over here, you can see that it's touching at more than one location. So this is not a function. The input 2 has more than one output. For this one, the input 3 has two different outputs. So this one is not a function. 3 is trying to go to two different locations at the same time, and that's not possible. This one, all of the inputs have their own output. It's okay for two different people to go to the same location, but it's not okay for one person to try and be in two places at once. So yes, this one is a function. Each input is assigned one output. That's the end of lesson 5. Check back in the playlist for more lessons from module 6.